National and international efforts to develop new sources of carbon-free energy are exploring a reactor concept first introduced in the 1950s and 60s. The Molten Salt Reactor. The first molten salt reactor experiments were conducted by Oak Ridge National Laboratory. The design was radical for its time and offered many advantages worth a fresh look today. Molten salt reactors differ from most nuclear power plants in operation today, such as light water reactors. To understand how, let's review the basics. Nuclear power plants generate electricity through a fissile chain reaction. Fissionable isotopes like uranium-235, 233, or plutonium-239 absorb a neutron and then fission, that is, split apart into fission products. In that process, they generate heat. As well, they eject more neutrons to continue the chain reaction. A moderator is usually employed to slow down the neutrons, so they are more likely to cause another fission when they impact the fuel. In the case of light water reactors, solid fuel rods contain the fissile material. Water surrounding the fuel acts as both a moderator and coolant. The coolant carries heat to turbines that generate electricity. In a molten salt reactor, the core operates very differently. The primary coolant is a salt heated above its melting point, so it is a fluid. While private industry is developing several distinct designs, here's the most commonly proposed configuration. Instead of fuel rods, fissile material is dissolved in the molten salt. The fuel flows around graphite rods, which moderate the energy of the neutrons to support the nuclear chain reaction. Other designs include liquid or solid fuel contained in rods, similar to current reactors, but with molten salt as a coolant. These reactors can use a broad range of fuel and salt compositions, and there are even designs that do not require a moderator at all and are a class called fast reactors. Several designs would employ thorium fuel, which offers many benefits. There is at least 3 times more thorium than uranium on the planet, and its waste largely decays in hundreds of years instead of tens of thousands. Other advantages of molten salt reactors include safety and efficiency. Replacing water as the coolant removes possibility of steam explosions and generation of flammable hydrogen gas. Low-pressure operation also places less demand on containment systems. The nuclear reactions are easier to control because liquid salt expands. In the event of an unanticipated rise in temperature, this expansion shuts down the reaction. Additionally, a freeze plug can dump the fuel into tanks and stop the reaction. This option provides a failsafe in the event of power outages or other events. Because these reactors can operate at higher temperature, their steam cycle generates electricity more efficiently. The use of liquid fuel allows for real-time waste processing. And finally, there is no need to shut down the reactor for refueling. New fuel can be introduced to the system during operation. While the test molten salt reactor of the 60s ran over a period of years, several challenges remain before construction and operation of a full-scale commercial plant. These include understanding and mitigating the corrosion of structural materials, development of reliable and efficient chemical separations, including tritium, instruments and controls for real-time monitoring of the reactor, and licensing and risk assessment for a non-light water reactor design. Researchers at Pacific Northwest National Laboratory are working on many of these challenges. We have expertise in radiochemistry, real-time online monitoring, as well as materials design and performance testing. Contact us to learn more about how we are advancing molten salt reactor technology.